So when the load is only applied, okay, the load is applied along the parallel to the neutral axis P over here, right? So this is what we consider axial loading. Okay, this is what we consider axial loading. Okay, so under axial loading configuration, the applied load P, okay, is acting inline or parallel to the neutral axis. So whatever I teach for this week and the next week is all based on axial loading condition only. Okay, axial loading condition only. You cannot apply when there's a bending. So a typical example of axial loading, as you guys have done this in static and dynamics before. Okay, a typical example you can see is we do truss analysis. Can anyone tell me what is truss analysis, please? Anyone, please? What do I mean by truss analysis? Anyone?
Is it to see how a truss acts when it's subjected to load?
Yeah, but when we assume an analysis to be truss analysis, what does it actually mean?
Method of joints.
That is an approach, but what else?
Analyzing the internal forces within the struts, within the truss.
Yep. Yeah. Also, yeah. Absolutely right. What else? Anyone? Okay. So when you guys, all your answers are right. Okay. All your answers are right. Somebody say method of joints and approach. Okay. All your answers are right. Nothing is wrong. So when we do truss analysis, we are unconsciously, or you were unconsciously, considering only what? You only consider axial loading condition. Okay, you ignore all the bending and you ignore all the shear force. You only consider axial loading. Now, let me elaborate myself. Okay, let me elaborate myself. So if we have a structure now, okay, we have a structure now with the following transformation. So we have a structure now. So this is my X, this is my Y, over here is my rotation about Z, and this is our transformation is based on the right hand rule. Okay, it's based on the right hand rule, right? So your thumb will be pointing towards you, and when you open up your finger, right, X to Y, you'll be touching X to Y, right? When you curl your finger, and you will curl your finger in this direction. So this is finger motion, right? That's why anti-clockwise is positive. So if we were to have a structure now, okay, so we have a structure. And then the structure over here, we have point A, and then over here we have point B, and then we have a certain length. Okay, so this is how our structure look like, and then another coming to here it's behaving, right? And this is what we call our point C. By the way, all these notes that I write will be uploaded onto Avenue immediately tonight. Okay, so if you want to sit back and not write anything, you could, or if you want to write something, you could also. Okay, and then you have applied load coming down, right? Applied load coming down over here, and this applied load is what we call P. Okay, so that's what we call P. So what we usually do is we are under Truss Analysis. Okay, when we do Truss Analysis, we are going to find the forces acting on members AB and member BC. Okay. So what sort of forces are we considering about? Okay, we are only going to consider axial forces. We totally ignore bending. We totally ignore shearing. And it's a simple form of analysis, nothing wrong with it. Okay. Then one of you decided, okay, Eugene, we want to go into methods of joint. Okay, you're absolutely right. We go into methods of joints. So we are going to do method of joints at point B. Now, before I go on, can anyone tell me is member AC in tension or in compression? Anyone?
Tension.
Tension.
Well done. So you all were saying that this is under tension. And member BC is under what? Anyone?
Compression.
Compression.
Compression, all compression. Wow. How do you know? Anyone? I know it's not easy to explain online, but how do you know? How come you know AC is tension, BC is compression? Anyone?
Well, BC would be in compression because P is basically pushing the truss or the member inwards, and AC is going to be in tension because the applied load is basically pulling it apart from at point A.
Okay, so you are basing it based on deformation, yes or no? Right? You are looking based on that. Yeah. So if I were to sketch out the deformation pattern, okay, so the structure was somehow, if you were to deform, it was somehow the P will come over here, the P will come down. Oops, I put it up, right? So the P will somehow come down this way, right? And then your structure will deform in this direction, right? So this is locked in, the structure will deform. Your structure will deform in this direction. I'm assuming it to be a straight line, okay? And then this will be in this direction. So that is why, so this is based on deformation. Okay, the green one, what I've drawn down here is based on elastic deformation pattern. Okay, you look at the deformation. So now some of you might, hey, I can't see it at all. Okay, I can't see why BC is in compression. So if you can't see it, don't worry. Okay, I'm going to teach you a way to analyze this based on physics. Okay, so just based on pure physics. Okay, so based on physics. Okay, before I go on, yeah, we're going to based on physics. So when we carry out method of joints, we are going to we are going to carry out static analysis. So when we carry out static analysis, means summation forces in the X, summation forces in the Y, summation of moment in the Z direction, all will be equal to what? 0. Okay. So we are going to apply the method of joints. Okay. So I'm going to have my point B over here. And then we have our applied load coming down. So this applied load coming down, this is my P. And then we are going to have our, so this line represent the member AB, and this line represent our member BC. Okay, so this represent our member AB, and this represent our member BC, right? So when we carry out methods of joints, okay, or truss analysis, we are just focusing on axial loading. So I repeat again, when we carry out truss analysis, okay, the focus is on axial loading. Because the green line that I've drawn, they can see over here, this is the neutral axis for member AB. And this line over here is for the neutral axis for member BC, right? Why is that? Because member BC, right? Why do I say that? Because member BC can only hold the what? Horizontal what? Okay, only hold the horizontal internal force. Yes or no? Right? It cannot hold any vertical load. The only one that could hold vertical load and horizontal load is member B, AB. AB can hold both horizontal and vertical load. However, it must be what? Must be
Parallel.
Yeah, there you go. Parallel to what? To the neutral axis. There you go. You were doing axial loading before. Okay. So based on methods of joints, right? Point B has a vertical load coming down. So we know now, we are very, very sure about this, is that we have AB, right? AB, I'm drawing this to, oops, shoot. Okay, fine. So this will be our ABY, right? And then because of vector, we have ABY in that direction. This will be our ABX. Okay. So when we apply static analysis, positive is going up, summation of forces in the Y direction is equal to 0, right? So what we have is ABY minus P is equal to 0. So we have ABY, which is equal to P, right? So when you know this angle over here, which is equal to theta, you know that from point B over here, this is your FAB. Okay, your FAB